Hello, and welcome back to another engineering problem video. In this video, I'm going to be going over a multi-differential equation problem of this reactor. So what we're working with here is we have a reactor that is a well-mixed system, meaning we have some sort of stir that's keeping all the solution within our reactor the exact same consistency. And we have a flow rate of some substance coming in at a specific temperature, which is different than the temperature of the substance that is already in the reactor. And we also have a flow rate coming out that is equal to zero point 0.4 times the height of the solution already in the reactor to the 1/2, or square root of h. And so the two things that are going to be changing within our well-mixed system is going to be obviously the temperature of the solution within the reactor, because we have a different temperature coming in than the temperature that's already in there. And the other thing that's going to be changing in our system is the height of our fluid, or the level of liquid in our reactor, because the rate coming in and the rate going out are not the same. So what we want to do is we want to set up two differential equations that demonstrate how the change in height varies with time, and the change in temperature also varies with time. So to get started, step one, I'm going to start with change in height with time. Well, the change in height of our reactor is going to be completely dependent on the amount of substance within our reactor. So it's going to be a mass balance. And like we know, a mass balance is just going to be the mass of our system is equal to the mass coming into our system minus the mass leaving our system. And we also know that mass is equal to density of our solution times volume. But in this case, we don't know the volume of a reactor, but we do know here the cross-sectional area of our reactor. So we can say that this is actually equal to density times cross-sectional area times height of our fluid in the reactor. So this will give us the mass of our system. So if we write this out, we can say density times area times height is equal to mass coming in, mass going out. That's going to be density times area times height times flow rate Q in minus density times area times height times flow rate out of the system. And remember, we're trying to find this as the change in height of our fluid in our reactor with respect to time. So I'm going to write this as d of density times area times height over dt with respect to time. And that's going to be our left side. So this is just saying that the mass of our system with respect to time. And over here, this area and height coming in, area and height going out, those can cancel. And I'm left with density times flow rate in minus density times flow rate out of our system. So what's next? Well, we know that it is a well-mixed system. And a well-mixed system means that it keeps all the solution within the reactor homologous. So we can essentially say that the density throughout our reactor is constant. It doesn't say anything where the density changes with temperature, and to keep things simple, we're going to assume that the density is constant throughout the entire time of the reaction. So that means I can get rid of density and just say that area times height with respect to time is equal to flow rate coming in minus flow rate out. And if you notice, we know that flow rate out is 0.4, times root h. So I can write this as 0.4 times root h. So there we have an equation that easily tells us that change in height with respect to temperature is equal to Qn minus 0.4 times root h. So the next step, I'm going to try and determine the change in temperature with respect to time. Well, the change in height with respect to time was a mass balance. So change in temperature with respect to time is going to be an energy balance. And an energy balance equation means Bernoulli's equation. So I'll write that out now. The change in mass, internal energy of the system, plus V squared over 2 plus GZ is equal to enthalpy plus V squared over 2 in plus GZ times change in mass in minus enthalpy out plus V squared over 2 plus GZ times dm out plus change in flow plus work non-flow. So to keep things simple, I'm going to say that we can ignore potential energy and kinetic energy, which leaves us with just dm, internal energy of the system, is equal to enthalpy in times change in mass in minus enthalpy out times change in mass out. There we go. Oh, and I need to remember that this is with respect to time. So the next step is that I need to better understand my enthalpy and my internal energy of my system. So H and U. And these can also be written with respect to specific heat times change in temperature and specific volume times change in temperature. So these are two heat constants that work with, when you work with a solution, they help understand how internal energy and enthalpy change with respect to the temperature of the system. So this would be Cp times some temperature minus some reference temperature. Here this would be Cv times some temperature minus some reference temperature. And this is just a range of temperatures from point 1 to point 2. So if I plug this in here, because I want to get temperature into my equation, it ends up looking like this. Change in mass times Cv, excuse me, times temperature minus reference temperature with respect to time is equal to, and then H becomes Cp times temperature minus reference temperature times change in mass in minus Cp times temperature minus reference temperature change in mass out. So that's taking enthalpy and internal energy equal to Cp dt and Cv dt, and plugging that into my equation that I derived from Bernoulli's equation. So the next step is I want to know what reference temperature I'm using. And I'm going to make it super easy on myself and say that the reference temperature that I'm using is equal to 0 Kelvin. So that way, I can say this is temperature minus 0, this is temperature minus 0, and this is temperature minus 0. And I'm just left with T. So this becomes just change in mass times CV times T with respect to time equal to Cp times T times change in mass in minus Cp times T times change in mass out. So what else can I do to try and simplify this? So I just get change in temperature with respect to time, similar to how I got this to change in height with respect to time. Well, I know that we're dealing with a liquid here, a well-mixed liquid. And when you're dealing with liquids or solids, your specific heat and your Cp and your Cv are the same. So when you're dealing with liquids or solids, Cp is equal to Cv. It's only when you're dealing with gases that Cp and Cv are different. Specifically ideal gases. So Cp and Cv vary when you're working with gases, but in a liquid or solid state, we can assume that Cp is equal to Cv. So here, Cp and Cp will be equal to Cv, so I can cancel them out in my equation. I'm just going to erase them. So I'm left with only change in mass times temperature with respect to time is equal to temperature times mass in times temperature times change in mass out. Well, just like I did here, I know that the mass of my system is equal to mass in minus mass out. And mass is density times volume, but in this case, density times area, cross-sectional area of the reactor, times height. So I can do the same thing and say this is density times area times height times temperature. And here, I can say this is going to be density times area times height times temperature minus density times area times height times temperature. This is in, this is out. I also know that because it's a well-mixed system, densities cancel. So I'll remove that. And I know that I forgot to add in flow rate. That's why I'm confused. So this is going to be area times height times temperature times flow rate in minus area times temperature times height times flow rate out. My mistake. This is that up here. I forgot to add that in. So just like I did here, I can cancel my areas and my heights for the right side of my equation. And I'm left with change in area times height times temperature with respect to time is equal to temperature times flow rate in minus temperature times flow rate out. And I know that flow rate out just 0.4 times root 8, or root h, excuse me. So, what I really want is just to get dh dt by itself and dt dt by itself. So, I want to get rid of the area here, and I want to get rid of area and height here. And I know that cross-sectional area is constant, but height is variable throughout the time of the reaction. So because area is constant, this is the easiest one to change first. So if I divide the right-hand side of my equation by A, or cross-sectional area, I can just get change in height with respect to time is equal to flow rate n minus 0.4 root h divided by A. And there, I have my first differential equation showing me the relationship between change in height with respect to time, which is what we were looking for. So delta H with respect to time. This one, on the other hand, is more difficult because I can still divide by area and get rid of the A on the left-hand side of my equation. But the height, or H, we already know varies with time. So we're going to have to do a little bit more complicated of a rearrangement. So first of all, I'm going to rewrite this by dividing by A and say that change height times temperature with respect to time is equal to T Q N minus T times 0.4 H divided by A divided by A. And what I want to do is change the left-hand side of my equation so that I can separate dt over dt and dh over dt. So I'm going to do that just like this. H times dt over dt plus t times dh over dt is equal to T Q N over A minus T 0.4 root H over A. And here, I've effectively separated dt over dt, change in temperature with respect to time, and now I just need to isolate that. So the first step is that I can subtract T times dh over dt and bring that over to the right side of my equation. So I'm left with H dt over dt is equal to temperature times flow rate n over area minus temperature times 0.4 root h over area minus, you can see, temperature dh over dt. So I've subtracted the temperature times dh over dt, moved it over to the right side of the equation. Now the only thing left to do is divide by h. So if I take everything on the right-hand side of the equation, divide by h, I'm left with change in temperature with respect to time. So this is my second differential equation. Showing me how temperature varies with respect to time of my reactor. So now that I've set up both of my differential equations from this problem, I can take these equations, bring them into Python Collaboratory, and solve for how our system looks throughout a certain period of time, and then plot out the change in height and the change in temperature. So now that we've solved for the two differential equations of our reactor for change in height and change in temperature, it's time to go into our code and start solving for the solutions and plotting them out
as functions of time to see what they look like. So I just opened a new set of code, and I've already brought in these. I'm just importing numerical Python, a science integration program for Python, and some programs for graphing from numerical Python, science Python, and plotly.io. The first step I'm going to want to do is begin with putting in my variables and assigning values to them. So first of all, I know that the initial temperature of the fluid inside my reactor is at 300 degrees Kelvin. So I'm going to say T0 or T0 is equal to 300. I also know that the temperature of the fluid coming into the reactor is a different temperature. It's higher. It's at 360 degrees Kelvin. So I'm going to say that Tn is 360. I also know that the constant cross-sectional area of the reactor is 1 meter squared. So I'm going to say A for area is equal to 1. And I know that the flow rate coming in, Qn, is going to be at 1 meter cubed per second. So that's going to be Qn equal to 1. I also know that Q out is going to be 0.4 times root h. And we actually get that from a 2gh to the 1/2 equation, which is the flow of liquid through an exit. But to keep things simple, I'm going to assign this as a new variable. I'm going to call it omega, and that is equal to 0.4. So I'll know that if I comment this in, 0.4 refers to a 2gh to the 1/2 equation, which we'll use this in reference to our h to the 1/2 when we start putting in our actual equations. So omega is equal to 0.4. I also know that the initial height of the fluid within my system is going to be 1 meter. And all of this reaction is taking place over a period of time. Because we use dt, it's going from 0 seconds to some set amount of time. So I'm going to say that my ending time is 100 seconds. So now I have all my variables, I can start bringing in my equations. So I'm going to start defining my x and y variables for my equations. So x is obviously going to be time. They're both dependent on time. And my two y's are going to be height and temperature. So I'm going to combine them and say that they're z. And I will say that I'm solving for height and I'm solving for temperature, and those are my two y variables. So h and t are equal to z. And I'm going to begin with my change in height over change in temperature equation. So my dh, just like I wrote out on the board, is going to be equal to flow rate coming in minus 0.4 times h to the 1/2. So omega times h to the 1/2. And that's all divided by the cross-sectional area A. So there, not add scatter, but A. So there is my change in height equation written out into Python. And now I'm going to do my change in temperature equation, which is temperature coming in times flow rate coming in, Qn, divided by cross-sectional area, minus temperature times 0.4 times h, so omega times h to the 1/2, divided by cross-sectional area A, minus, and then I had temperature times dH over dt. So temperature times my dH equation, which is here, my other dependent, or my other differential equation. And all of that was divided by height, h. So there is my change in temperature equation, which I solved for on the whiteboard, and my change in height temperature, or change in height differential equation. So if I set this up as my numerical Python array, I hit return numerical Python array, and this is for dH and dt, change in temperature and change in height of the fluid in my reactor. So shift enter. Oh, I need to define this as a right-hand solution. Excuse me. So that's defined as the right-hand solution of T and Z, Z being height and temperature. There we go. So now I've defined my two differential equations. The next step is I'm going to solve for them. So I'm going to set them up as a solution. So SOL solution is equal to, and here I'm going to use my solve IVP that I took from sciencepython.integrate. So solve IVP for my RHS, my right-hand solution. And then now it's asking for my T span, so my time span. So that's going to be from 0 seconds to 100 seconds, which I set up as T end. Yeah, so T underscore end. T underscore end. And now it's asking for a Y0. So I just gave it my T-span. Now it's asking for, it should be asking for a Y0, which is my numerical Python array of DH and DT. So np.array of DH, comma, DT. And then it's asking for method. So I'm going to be using the Radow method for this. And now it should be asking whether or not the dense output should be equal to true or false. So my dense output is going to be equal to true. Dense underscore output equal to true. And this will help when we're plotting out our two equations later. True. And then dot solution. There we go. And now I need to set up a plot for my time. So T plot is equal to, I'm going to be using the linspace here. So T plot equal to linspace, numerical Python. Oh, so np.linspace of 0 to T end, so 100 seconds, and so start, stop, and then some number in between them. So I'm going to say that there's 400 points between that. Between 0 and 100 seconds, I want 400 data points. So every quarter of a second. And then my height and temperature will be set up through the solution of my time plot. Shift enter. DT, DH is not, it says DH is not defined. Oh, okay, so this should not be DH and DT. It shouldn't be my equations. It should be my initial conditions for height and initial conditions for temperature. So my height initial is H naught, and my temperature initial is T naught. So this is going to be H naught, T naught. There we go, now it works. And my last step is to set up my figures so I can see them as they're plotted out as a scatter plot. So I'm going to do fig dot, or fig is equal to, I'm going to make subplots on time equals 0 to T end. No, I've already done that. I'm going to make my subplots. Oh, and it's telling me I need to do rows and columns. So because I have time on my x-axis and height and temperature on my y-axis, I'm going to have one row and one column with my one row being temperature and my two columns being height and time. So rows equal to 1, columns equal to 2. And now I can set up my two figures of change in height and change in temperature. So fig dot add, and I'm going to do a scatter plot. I'm going to have my x-axis and y-axis. So my x-axis is obviously going to be time. So my plotted time, which I said is t plot. And my y-axis for my first scatter plot is going to be change in h. So y is going to be equal to, should be h. And it's going to be row 1, column 1. So row 1 being temperature, column 1 being height. So row equal to 1, column equal to 1. And then the same exact thing, making my second scatter plot for time. So fig.add scatter. My x is still going to be my plotted time, so t plot. Y is now going to be equal to temperature. The row is still going to be 1 for temperature, and the column now is going to be 2 for time. So shift enter. And there we go. I can easily see here that starting at time equals 0 to 100, I go from 1 all the way to 6. So I'm starting at height of the fluid in my reactor at 1, goes up to 6, and it levels off right around, I want to say 60 seconds. And here, my temperature starts at 300 degrees Kelvin, and it rapidly rises and gets all the way up to a constant 360 degrees in about 20 seconds. So I can go back through and change the amount of data points in between here. Let's say to 700. I want 700 data points between 0 to time end at 100 seconds. Shift enter. I do this again. It could give me a more accurate representation. So there we go. I've taken the two differential equations from the reactor with change in height and change in temperature. I've brought them into Python Collaboratory, and I've been able to plot them out as graphs with respect to time from 0 seconds to 100 seconds.
So coming back to another reactor problem, we're given this problem where it seems very similar to the one we just dealt with. We have a flow rate going into a reactor that is a well-mixed system. We have a flow rate coming out at 0.4 times root h. We have the height of the fluid within our reactor, and we have a cross-sectional area of our system. But if you take a closer look, now it's telling us that we have a specific concentration of fluid coming into the reactor and a specific concentration of fluid coming out of the reactor over a period of time. So here, very similar to what we just did, we are trying to find the change in height of the fluid within our reactor with respect to time. But now we're also trying to find the change in concentration of the fluid within our system with respect to time. So in the previous problem, we did temperature, but now we're working with the concentration. So essentially what it's telling us is that before this reaction takes place, we have some initial concentration, C naught, of solution already within our reactor at time equals 0. And as soon as the reaction starts and we have a solution or solute coming into our reactor, it has a different concentration. And then this becomes the concentration of our reactor, and then we have a specific concentration coming out. So we want to figure out how not only the height of our reactor varies with time, but the concentration coming out of our reactor varies with time. So to start this off, I'm going to do what we've already done find change in height with respect to time. Well, just like we did in the last problem, we know that the change in height, or the level of fluid within a reactor, is a mass balance. And we know that mass is equal to density times volume, or in this case, volume will be area times height. So again, with respect to time, this is going to be d of density times area times height, or dt with respect to time, is equal to mass in minus mass out. So density times flow rate in minus density times flow rate out, where the areas and the heights cancel. We also know, again, that it is a well-mixed system, so we can assume that density throughout our reaction is constant. So that eliminates density from both the right-hand side and left-hand side of our equation. And we are left with just area times height with respect to time is equal to flow rate in minus flow rate out. And we know, just like last time, that flow rate out is 0.4 times root h. So from our mass balance, now we know, again, how the change in height of our fluid in our reactor changes with respect to time is equal to flow rate in minus 0.4 root h. Now, pretty simple stuff we've already done in the beginning of the video. So step 2, which will be the more difficult step, is understanding how concentration changes with time. So similar to how step 1 and the change in height of our fluid was a mass balance, the change in concentration of our system, or the fluid going through our system, is going to be a material balance. So we're going to have concentration times area times height to find the concentration within our system. It's going to be equal to concentration times density times flow rate in, concentration in, minus concentration out times density times flow rate out of our system. And again, this is with respect to time, so d over dt. So this is our material balance. Well, one thing we can figure out right off the bat is that we have a C out here. And if we know that this is a well-mixed system, we can assume that everything, all the fluid within our reactor is homologous. It's exactly the same. There's no chunking or floating material. It's completely well mixed. So anything within the system should be the same as anything that's leaving the system. So anything coming out would be the same at that time or at that second as whatever's inside the system versus what's outside the system. So we can assume, because this is a well-mixed system, the concentration within our system is equal to the concentration flowing out of the system at any given time. So I can rewrite that here and say that C out is really just concentration. I've also already stated that the density, that's supposed to be a density, not a Q, my mistake, that the density is constant. So this just becomes, this gets removed from the right-hand side of the equation. And we know that change in concentration times area times height with respect to time is equal to concentration in times flow rate in minus concentration out, which is concentration times flow rate out. And we know flow rate out is 0.4 root h. So to simplify this side, the left side of our equation, because we just want to have dc over dt, the change in concentration with respect to time, I'm going to divide the cross-sectional area over to the right-hand side of our equation, because the cross-sectional area does not change with time. So, save some space. I divide over by A, I'm left with change in concentration, height, with respect to time, is equal to concentration in, times flow rate in, divided by area, minus concentration times 0.4 root h divided by area. So now we have this equation and this equation. But I'm only looking for change in concentration with time and change in height with time. So here, I can easily get dh dt alone by dividing by a. So that just becomes change in height with respect to time is equal to flow rate in minus 0.4 root h divided by a. And there I have my first differential equation showing us the change in height with respect to time. This one, on the other hand, is more complicated because I can't just divide over by height to get dc over dt, because height is also changing with time. It's already a differential equation. We know that the height is going to be changing as this process occurs. So I need to change the left-hand side differently. I'm going to split that up by saying concentration times dh over dt plus height times dc over dt is equal to Cn Qn divided by area minus C times 0.4 root h divided by area. Now I can isolate change in concentration with respect to time. First, I'm going to subtract C times dh over dt, bring that over to the right side of my equation. So it disappears from over here. And now I can simply just divide by height. So divide this entire right-hand side by h. And I'm left with just change in concentration with respect to time on the left side of my equation. And here I have my second differential equation that shows me the change in concentration in my reactor with respect to time. So just like I did with the first problem, using height and temperature, I'm going to take these equations and bring them into Python Collaboratory so I can solve and plot for change in concentration and change in height.
So now that I have my two differential equations for concentration over time and height of the fluid in my reactor over time, I can begin bringing in those equations and my variables into Python Collaboratory and start solving for them and plotting them out. So first of all, I've already imported numerical Python as MP. I've imported sciencepython.integrate to solve my IVP and my right-hand solution. And I'm also using plotly.subplots so I can plot them out and plotly.io. So the first step I'm going to want to do is start bringing in my variables. So I know the concentration in is going to be 1 kilogram per meter cubed. I know that my initial height starting in the reactor is going to be at 1 meter. I also know that my initial concentration is going to be at 0.1 kilograms per meters cubed. And I know that the 0.4 that I was using in front of my height to the 1/2 is going to be equal to, it is 0.4, and that comes from the 2gh all to the square root value. So I'm going to be calling that 0.4 omega here. And just so I don't get confused, I'm going to make sure I comment that. And that comes from the 2gh to the 1/2 equation, so that will be equal to here omega times h to the 1/2. Next up, I'm also going to be knowing that my cross-sectional area is equal to 1 meter squared of my reactor, and that stays constant throughout the equation, or throughout the reaction, excuse me. And I know that my reaction is going to take place from time equals 0 to 100 seconds. And then lastly, I also need to know that the flow rate coming in is about 1 meter cubed per second. So I've set up my variables, and now I can start solving my problem. So I'm going to start by defining the right-hand side of my equation with the x being time, and my two y components is going to be concentration and height. So I'm just going to call that z for now, and then I will say that concentration, or height and concentration, is equal to my z, not z, is equal to z. And now I can start bringing in my two differential equations. So the change in height, or dH, is going to be equal to my flow rate in, which I already set up here as my variable, minus my 0.4 times h to the 1/2. So that's going to be omega times h to the 1/2. And that's all going to be divided by my cross-sectional area A, and that's my first equation for change in height with respect to time. And then my next equation, change in concentration with respect to time, is going to be equal to concentration coming into the reactor times flow rate coming into the reactor minus, or divided by area, minus, I'm going to have my 0.4 times height to the 1/2, so that's omega times h to the 1/2, and that's also going to be times concentration, C, divided by cross-sectional area, again, minus concentration times, here I brought in the dH, which is the first differential equation, change in height. And then all of that is going to be divided by height again. So I have my two equations, so now I can return for my numerical Python array of time, concentration, and height. And that's going to be brackets of dH, change in height, and dC, change in concentration. So shift enter. There we go. I've defined my two differential equations. So now I can start solving for them. So if I set up solution equal to, I'm going to be using the solve IVP that I imported from Science Python. So solve IVP of my right-hand side equation from, I'm going to be using from my time of 0 to 100 seconds, which I set up as t end here. And then, okay, and then my numerical Python array, which I already set up here, is starting out at height 0, which I said, or height initial, excuse me, which was 1 meter, and concentration initial, which was 0.1. Oh, I need brackets and parentheses there, okay. And I'm going to be using the Radow method. That's how I spell it, okay. And I'm going to be setting my dense output equal to true, which will help with plotting these later. And then sol, and then my time plot is going to be from my numerical Python linspace, which I also made up here, from time equals 0 to t end, and I'm going to put in 600 for now. And I'm going to have my height and concentration be equal to my solution of my time plot. See if that works. Okay. So I've set up my solution, I've set up my time plot using time equals 0 to time equals 100 seconds with 600 points in between each. And now I just need to create my figures. So fig equals make subplots. And because I have both change in height and change in concentration, I'm going to have rows equal to 1, which is just time, and columns equal to 2 for height and concentration. I'm going to want scatter plots, so I'm going to add scatter plot with my x being equal to time, so my time plot. My first y is going to be equal to height of the fluid within my reactor, and this is going to be still row 1 because of time, and column 1. And I do the same thing for my concentration. So my x is still my time plot, and my y is my concentration, and row 1 is still equal to 1, but now my column is equal to 2 because it's my second y. So I hit Shift Enter, see, make subplots. Oh, I put it, that's supposed to be a underscore there. Oh, spelling error, t-plot, not t-ploy. And there we go. I have my two plots of change in height and change in concentration. Here from 0.1 concentration to about 1 over the course of 100 seconds, and change in height over the course of 100 seconds. So there, I've taken my two differential equations, I've put them into Google Colab for Python to find the right-hand solution. I've solved for the IVP, and I've created the scatter plot figures over the course of 0 seconds to 100 seconds.